Additive manufacturing, or metal 3D printing, is often celebrated as the future of production. We've all seen the headlines around printing rocket engines, printing implants, printing spare parts on demand. The promise is clear: faster, cheaper, more flexible. But here's the uncomfortable truth. When you actually run the numbers, additive manufacturing isn't always cheaper. In fact, in many cases, it's more expensive than the traditional processes it's supposed to replace. So, how do we cut through the hype and really understand the economics? That's what today's episode is all about. We're going to break down the true cost of additive manufacturing, from the price of the machines to the materials to operations and post-processing. Then we'll compare AM with traditional manufacturing and ask, when does it actually make sense? And we'll look at real-world use cases where the cost-benefit balance tips in favor of AM. Because in the end, the question isn't just can we print it, it's should we print it, and when does it pay off? So let's dive in. To understand the economics of AM, we first need to talk about what actually makes it expensive. When you peel it back, there are four major categories of cost: capital investment, operations, materials, and post-processing. Each one has its own challenges, and when you add them together, you start to see why AM isn't always the cost saver people imagine. Let's begin with capital investment. The machines. A high-end metal printer, whether it's laser powder bed fusion, electron beam melting, or directed energy deposition, comes with a serious price tag. At the low end, you might spend 200,000 euros, but at the top end, $1 million or more. And of course, that's just the machine. To run it properly, you need a whole supporting ecosystem: inert gas systems to prevent oxidation, powder handling equipment, ventilation and fire suppression systems, even protective gear for staff. Some facilities go further and build climate-controlled rooms to stabilize humidity and temperature. And then you have the software: design optimization, build simulation, slicing, in-situ monitoring, all licensed at enterprise rates. So before you've printed your first part, you've already spent a small fortune. And unlike traditional machine tools that last decades, AM systems evolve quickly, so depreciation and obsolescence are very real. Once you've made that investment, you move into the challenge of operations. Metal additive manufacturing is energy intensive. High-powered lasers or electron beams often run continuously for dozens of hours, sometimes over 100, to complete a single part. That's a lot of electricity. But the bigger cost is people. AM requires highly trained operators and engineers who understand metallurgy, digital workflows, and process monitoring. They prepare build files, orient parts, optimize supports, and troubleshoot issues mid-build. And then there's maintenance. These machines are complex, full of optics, sensors, and recoaters that need calibration. When downtime happens, it's costly, and a failed build means wasted material, wasted time, and often an unhappy customer. Operationally, AM is far from push-button simple. Then there are the materials, and this is where many people get a shock. Metal powders are dramatically more expensive than bulk stock. Take titanium alloy Ti 6-4, as bar stock, maybe 40 euros a kilo. As AM powder, 200 to 400 euros a kilo. The reason is strict quality control. Powders need spherical particle shapes, tight size distribution, low oxygen content, and excellent flowability. Producing this quality requires sophisticated atomization processes. And here's the catch: you can't reuse powder indefinitely. With each build, oxygen and nitrogen exposure degrade it. Some particles fuse or oxidize. After a few cycles, you have to discard a portion of the batch. For big builds, that adds up quickly. Materials alone can be a major portion of the cost. Finally, we get to post-processing, the hidden giant. Printing is just the start. Almost every part needs heat treatment, and high-value ones often require hot isostatic pressing to close porosity. Critical surfaces are machined because current AM can't deliver the tolerances required. Many parts need polishing, blasting, or coatings. And then inspection. In aerospace or medical, you can't just look at the part. You need ultrasonic inspections, CT scans, or full non-destructive testing. By the time you're done, post-processing often accounts for 30 to 50% of the total cost. So when you combine all of this, machines, operations, powders, and post-processing, it's clear why AM carries a hefty price tag. It's not just a printer and a bag of powder. It's a whole ecosystem. Which leads to the real question, compared to what? When does AM make sense, and when is traditional manufacturing the smarter choice? So let's compare, because the truth is, in some areas, AM can't compete on cost, but in others, it delivers advantages conventional methods can't touch. Take tooling. In casting, forging, or injection molding, the cost sits up front in the tool. Molds, dies, patterns, they're expensive to make, but once you have them, your cost per part plummets as you mass produce. AM flips that equation. No tooling, no dies, no dedicated setups. Straight from CAD to part. That's a huge advantage if you only need a handful of components, like custom titanium brackets for an aircraft. But if you need 10 million plastic bottle caps, tooling still wins hands down. Material efficiency is another comparison point. Traditional machining wastes huge amounts of material. An aerospace titanium bracket might start from a billet where 90% becomes scrap. That's a buy-to-fly ratio of 10-to-1 or worse. With AM, you're building up material exactly where you need it. That ratio can drop to 2-to-1 or even 1.5-to-1. When the raw material is as costly as titanium, those savings really matter. Labour and complexity play a role too. Traditional manufacturing often requires multiple steps. Cast the part, machine it, drill, polish, assemble. Each stage costs time and money. AM can consolidate that. Instead of 3 bolted together pieces, you print one monolithic part. You save labour and eliminate weak points. Of course, the labour shifts into design and build preparation, but the overall chain is often shorter. Speed is a nuanced one. AM looks slow when a part takes 3 days to build, but the real advantage is in time to first part. Traditional tooling can take weeks or months to design and qualify. AM skips that completely. For urgent spares or patient-specific implants, the ability to go from file to part in days is invaluable. And then there's scale. Traditional manufacturing dominates high-volume production. Stamping out millions of identical car parts will always be cheaper with presses and molds. But AM doesn't need scale. Its strength is economies of scope. The ability to make small batches of varied, complex parts without extra setup costs. So when does AM win? It wins when the part is low volume, but high value, when the geometry is complex or impossible to machine, when customization is essential, and when speed matters more than unit cost. Traditional still owns high-volume, low-margin work. The point is, AM isn't replacing conventional manufacturing. It's complementing it. It's filling the gaps where traditional methods can't deliver. Which naturally leads to the next question. Where does the cost-benefit analysis actually tip in AM's favour? What are the real-world examples that prove it pays off? This is where things get interesting. AM isn't about being universally cheaper. It's about winning in the right contexts. The first context is high-value, low-volume industries like aerospace, defense, and medicine. In these areas, you're not making millions of parts. You're making a few hundred, maybe a few thousand, and each one is worth a lot. Take GA Aviation's LEAP engine fuel nozzle. Traditionally, it was 20 separate parts brazed and welded together. With AM, it became one monolithic part, lighter, stronger, more reliable. Machine time was expensive, but in the context of a jet engine, the economics worked beautifully. The second strength is geometry, as traditional methods hit limits with complex shapes. AM doesn't. Think of conformal cooling channels inside injection molds, nearly impossible to machine but straightforward to print. Those channels cut cycle times, reduce rejects, and pay back the higher insert cost in months. Or think of spinal cages with porous lattice structures that encourage bone ingrowth. Not feasible by machining, but routine with AM. Then there's customization. Traditional thrives on sameness. AM thrives on uniqueness. Medical implants are the clearest case. Standard implants work for many, but not all. With AM, surgeons can scan the patient, design a custom implant, and print it. Yes, the unit cost is high, but the alternative, trying to machine a one-off implant or forcing a poor fit, is worse. The same applies to aerospace spares or custom tooling. Supply chain agility is another win. Instead of stocking thousands of rarely used spares in warehouses worldwide, companies can store digital designs and print on demand. Lufthansa Technik has demonstrated certified AM cabin spares this way. The military has tested printing spares at forward bases, avoiding long and costly supply chains. The cost advantage isn't just in the part. It's in the logistics. And then there's sustainability. AM can save huge amounts of material, particularly in titanium aerospace parts, where traditional machining wastes 80 to 90%. Shorter supply chains mean fewer transport emissions. But the picture isn't simple. Those lasers and HEP furnaces consume a lot of energy. So AM isn't automatically greener. It depends on the context. If you're saving 9 kilos of titanium scrap per part, that's a win. If you're printing something simple from cheap aluminum, maybe not. So let's ground this in some practical examples. That GE fuel nozzle, from 20 parts down to 1, lighter and cheaper to assemble. Airbus cabin brackets redesigned with AM, shaving weight that translates into lower fuel consumption over an aircraft's lifetime. Cranial implants that fit patients perfectly, designed from CT scans. Turbine blade repairs using directed energy deposition that extend service life instead of scrapping the blade. Or injection mold inserts with conformal cooling that pay for themselves by reducing cycle times and scrap rates. These are the cases where AM makes sense, when the part is high value and low volume, when the geometry is impossible by other means, when customization delivers real benefit, when supply chains need flexibility, and when material efficiency outweighs the energy cost. That's why, despite the higher upfront costs, AM is spreading across aerospace, medicine, energy, and tooling. The economics don't work everywhere, but they work exactly where they need to. So where does that leave us? Additive manufacturing isn't automatically cheaper, and it isn't here to replace every traditional process. The true cost comes from the whole ecosystem: the machines, the operations, the powders, and the post-processing. On a per-part basis, AM is often more expensive, but when you factor in eliminated tooling, reduced material waste, complex geometries, customization, and supply chain agility, AM starts to shine. Its strength isn't competing on unit price, it's competing on value, delivering what's impossible or impractical with conventional methods. And now I'd love to hear from you. Where do you see additive manufacturing delivering real cost advantages? Is it in aerospace, in implants, in tooling, or in the way it reshapes supply chains? Share your thoughts in the comments, tell me your examples, or even point out where you think AM still falls short. I'll feature some of your insights in a future episode. If you enjoyed today's discussion, don't forget to subscribe so you don't miss the next one. And if you found it valuable, share it with a colleague who's wrestling with the economics of AM. Thanks for listening, and I'll catch you in the next episode.